Hello, this is a short mini lecture, maybe 10 minutes tops, where I talk about normalisation, what it is and why we bother with it. And the aim of this is to give an overview before we do normalisation in class. So it's just a kind of preview of what we're doing and motivating it. I'm not going to cover how to do normalisation, that's what we're going to do in class. So, what is normalisation and why do we bother with it? To begin with, normalisation is a process. It's a process which takes data which could be from different sources, it could be disorganised, it could be from multiple sources, it could just be a problem that we haven't come across before, and then what we do is we analyse that problem and we analyse the data and turn it into a form that is appropriate for storage in a relational database. Normalisation involves steps. It involves the steps of converting your data first into first normal form, then into second, then into third, and each of these steps has got a quite well-defined process. So the aim of normalisation is to take your data through these steps until you end up with the organisation that works with a relational database. But why do we do it? That's the question I want to tackle before we start. It's a procedure, so databases sit on a theoretical underpinning, but normalisation isn't a theory. Normalisation is a procedure. It's steps that you follow. If you follow these steps, you end up with a normalised database. It sits on theory, but it's not a theoretical activity. If you understand what first normal form is, second normal form is, third normal form is, you will know the procedure for transforming your data from a disorganised mess of data, is that a term, to something that you can then use within your data model, your relational database. Why do we do it? It reduces redundancy, so things aren't stored in the database twice. It increases integrity, which means that your data is more likely to stay in a situation where it hasn't been changed by system errors or by user error or anything like that. And it does this through reducing the chance of, or avoiding completely the chance of, insertion anomalies, deletion anomalies, and update anomalies. And I'm going to look at those a bit more briefly now. What we do, this is a quote from E.F. Codd's paper on normalisation, which was written in 1972, which is quite a long time ago now. And this is, in Codd's words, why we do normalisation. Remember, we're talking about relations here, so a relation might look a bit like a table. But what we're doing is we've got a collection of relations rather than a set of tables. And that's because relations have various properties that we talked about last week. But by normalisation, what we do is we get rid of the possibility of insertion, update and deletion dependencies. We reduce the need for restructuring the collection as new types of data are introduced. So if we know that our data is organised and we need to add another data source or another type of thing, because we know that the original data is normalised, adding new data is much more straightforward. It makes the model more informative to users, so you don't need to have, if it's properly normalised, it should be easy to understand, and to make it neutral to the query statistics. So this means you're not optimising for a particular type of query with a normalised database. So that's what Codd said, but now I'm going to talk about a little bit about what that actually means in practice. So if we want to reduce data redundancy, what we're going to do is we're going to try and minimise repetition. So what I've got here is a student database, and a student database that's very, very badly designed. So what we've got is 3 students, Tom, Frian and Elvis, and they're doing various modules, courses. The courses have got IDs, the students have got IDs, and they've got an address, and their courses have got names. So the first thing we do, one of the things we do when we normalise is we determine if an attribute can be determined from the value of another attribute. If this is the case, we move it to a separate table so we don't get repetition. So one of the things we've got here is we've got course ID, and course ID and course are always going to be the same, right? So when course is 270, the course is always going to be databases. When course is 241, the course is always going to be pictures. So there's redundancy in there. So if you can determine the value of a data item from another data, we move it to a separate table. Another problem we have is insertion. So if all of our data is kept in a big relation like this, we can't insert a new table, new course, if we don't have any students to put it in, put on it. So if we added a new course, let's say CS 312, we could put CS 312 in the course ID, and we could give it the name, Modelling, Managing, Securing Data. But we wouldn't have any entries in the student tables. What happens if we've got a student, but we don't know their address? We can't have empty things in the table, so we can't add them. And this is what we call an insertion anomaly. Then there's update anomalies, right? So if we have the module 270 and instead of being databases, it becomes, I don't know, SQL. What we could do is we change it in one place, and that's fine, but we'd actually have to change it in 3 places. If Tom moves house, Tom's in the database twice because he's doing 2 modules. If he moves house, if he moves house, we'd have to remember to change his address in every row. So keeping our data up to date is problematic. And finally, there's deletion anomalies, and this is like a partner to the other ones, right? So if we delete Tom and Shian, they're the only people on this module, we could lose the information about the module. This is probably not what we want. Ideally what we want is for information that depends on other information to be kept separate, in separate relations. Here's a summary of those 3 anomalies that we want to avoid. The first one is update. So with an update anomaly, if you update data that's repeated, you have to remember to update every single instance of that data. The second one is an insert anomaly, and that says that attributes can't be inserted into the database without the presence of other attributes. And finally, there's a deletion anomaly, which means you can lose data altogether if other unrelated attributes are deleted, if it turns out that what's happening is you're storing data against things that it doesn't really depend upon. So if we look back at this example of the deletion, if we remove Tom and Rianne, you've got a dependency, so courses are depending upon students, and that's not the way around it works. Courses are independent, students are independent. You could have a course that didn't have any students on it, you could have students that weren't doing any courses on them. So what we do when we're normalising is what we're doing is a process that ensures that no element of data in our data model depends upon things that it doesn't have to depend upon, and also that there's no repetition. Through doing this, we avoid these anomalies. How do we do it? What is it? That's the topic of the week. We're going to start by making sure that every single piece of data is atomic, so we don't have any lists or groups of information within any of our table cells. That is, every attribute for every tuple in our relation is as simple as it can be. Then what we're going to do is we're going to go through these steps: first normal form, second normal form, third normal form, to work out what data depends upon what other data, and that will enable us to have these normalised outcomes.